Last class we designed the current loop of our closed loop control of our AC-DC converter. Now, from the current control design, we have to go to the voltage control design, that controller design. So, again let me draw our closed loop control schematic for clarity. So, this is our V0 reference, that is the one we want. This will be giving it here, then we will be comparing with a feedback voltage, that is V0, then we will give to the current controller. So, this is our controller, this we have to design now, controller. Okay. This controller output will give our IS reference. This is your feedback, then your current controller. Current controller, what we got? This is a proportional gain only you require. So, what we got here, it is equal to K1 is equal to L divided by Ki G into T. T is the first order lag. Okay. G, this will go to our converter. Converter we have got it as G by 1 plus ST R. R is the triangular period. So, we are representing as a first order lag. Then here you will get the actual fundamental component of the VAB. So, this minus Vs, okay, that Vs we are not considering here for the controller design, because controller design is based on our input IS star. So, that will remove as a disturbance input, and then the closed loop block diagram will be 1 by SL, then you have this one, current feedback Ki comes here. This is our current loop. Now, how we design the voltage loop? So, voltage loop, this current IS is based on the output DC current, load current. So, we should have a relation between this IS and the output DC. So, equating the real power, input power should be equal to the equating input power to the output power. Power equal to the output power we will find the relation, that is Vs, that is our V input RMS. Okay. If this is the maximum value, this V divided by root 2 into IL peak value, these are peak value, I load our IS peak divided by root 2 is equal to V0 into I0, I0 is output DC. From this one, I0 is equal to V IS, these are peak value, into 2 into V0, this is the I0. So, this I0, if there is no change in load, this I0 will go to the load and the capacitor voltage will be stable. If any mismatch in the, if there is sudden change in the load happens, it has to be reflected. The controller should know that, and based on that it should adjust the IS to so that the capacitor voltage should not change it. So, the block diagram for our voltage loop is like this. Maybe we will draw with a different color. So, we will take it from here, this is our IS, Is, this is a gain block. This gain is this much only. 2V by V0. V is our input voltage. So, V by 2V0, we get our I0 here. Plus minus. This is our actual I load current. If there is any change in, if there is no change, this I0 will be equal to I load, this difference will be 0 and the capacitor voltage will be stable. If any change in I load happens, this I0, the flow I0 will disturb the capacitor voltage. So, that difference will go to the capacitor and it will disturb the capacitor voltage. So, that will be 1 by C integral. That will give the V0. Change in V0 plus V0, the change in V0. Then you have the gain kV. This is the one we will give it here as feedback. Okay. Now we have designed our control loop here. Yesterday. And we got the transfer function. If you see here, Is by Is star. This Is by Is star is equal to star is equal to 1 by Ki divided by S square plus 1 by Tr into S plus 1 by Tr. And we also found out for a damping theta is equal to 0.707, T should be equal to 2 Tr. Okay. Now, see this, let us write down in a different way. This can also be written as 1 by Ki divided by, that is time constant from fluid, 1 plus St plus S square Ttr. Okay, S square Ttr. So, if you see here, this also in a different way we can write it. This S square Ttr, these are frequencies multiple, these are the square of frequencies. So, this current loop is in this closed loop, the current loop should act very fast compared to our voltage loop. So, that means the frequency response of this one is much higher compared to this voltage loop for fast action. So, if when you consider the voltage loop, now we have to design the voltage loop. See, these higher frequencies which will be much beyond the response range of this current voltage loop. So, this current loop we can approximate as, that is Is divided by Is star, we can approximate to design our voltage loop. This is 1 by Ki divided by 1 plus St. We know T is equal to 2 Tr. So, in general time. So, we can use this one. So, from this one, that means whole this block here circled by the green line, we can represent by 1 by Ki by 1 plus Str. So, from this one, let us draw the voltage loop. Okay, voltage, the block diagram of our voltage loop. let's go to the next page. You have V0 star, our reference again, plus minus, then our controller. So let us again take for controller with the, for good dynamic response. Let us take the PI controller. See, here we get the I0 that this point. Sorry, this point will get the I0. This I0 minus I load, if there is a disturbance in load, the difference will go to the capacitor. So let us take a worst case design where full I0 is going to this capacitor, so that we can assume I load is 0. Then we will try to design our controller. So if you go back to our controller, okay, we will assume worst case condition I load is equal to 0. So the full I0 will go to the capacitor, so it will be 1 by SC. This is our actual V0. This V0 will put with a gain to bring to the controller gain, that is kV, and feed it here. This is our closed loop controller. Now again let us see what is the purpose of this lead. There is a lead here, 1 by 1 plus STN. So if you write down the transfer function, that is V0 by V0 star is equal to GS by, that is forward gain divided by 1 plus forward plus closed loop gain. This will be Kn into 1 plus STN divided by STN to 1 by Ki divided by 1 plus ST. Let us take V plus V0 as some constant V1. So this we will take it as a some constant V1. V1 by SC divided by 1 plus Kn into 1 plus STN divided by STN to 1 by Ki 1 plus ST V1 kV by SC. Now if you use the pole 0 cancellation, so that this 0 which will say will give a lead, we can choose Tn such that we can remove this lag due to 1 plus ST, so that response can be faster. So if we cancel this one, again if you write down the transfer function in the denominator, if you see here, S square term will be there, S term damping will be missing. So if you use the pole 0 cancellation here, this system will become unstable. So we want this, we want to keep this controller, so that in steady state error should be 0 and we should have a good bandwidth. Now how do you choose our Tn and Kn in this case? Now let us say here you will use some sort of optimization technique. What is the optimization technique? See, we will make the definition. What is mean by optimization? See, general consideration for optimization. For optimization. See here, what we want in a closed loop control, the input should follow the output for any variation in the input as fast as possible. That is, any variation means any frequency of response. See, for a system, input cannot change with any frequency of variation. So, system may not be system dynamic, system time constant will not allow. So, with the system time constant, there is a frequency limit up to which input can vary. That shows the bandwidth, such that the output should vary as close as possible to the input. That means the input output gain should be, for wide frequency range, it should be unity. That shows the bandwidth. So, this optimization aims at choosing Kn and Tn such that the bandwidth can be extended as far as possible. So, let us have what is the definition? The dynamic performance of a control system is good if the controlled variable rapidly reaches the reference input. This means for any frequency within the bandwidth, any frequency of input variation the output should track the input variable, or in other terms the output should track the input variable instantaneously. So, for a practical system, in terms of frequency range, the modulus of the output or the output gain should be close to 1. That means, if you say that it should be if it is tracking the input divided by the IS, that modulus should be as close as to 1 over a wide frequency range. That is the bandwidth. So, if you draw the gain, that closed loop gain, let us say this is in log omega, omega here, and the gain modulus input output gain should be 1 for large frequency range. As the frequency increases, this will slowly change. So, this will show the bandwidth. So, bandwidth of the system, that frequency range, we want to optimize by choosing Tn, our controller gain, such that we should have maximum bandwidth. That is another way of choosing our parameter, controller parameter. So, the optimization, what is this optimization is planning? Now, we will talk about the optimization. Aims at bringing the bringing the input output gain as close as to 1 over a wide, bringing the gain, over a wide frequency range. This is also called modulus hacking. So let us see how we can do. That is, let us take the closed loop transfer function for a general second order and general third order. So we will restrict to these two, and then how we can do the optimum bandwidth, maximum bandwidth. That's the modulus input output gain is as close as to 1 for wide frequency range. Let us take the second order system. Let us take the general transfer function, B0 divided by A0 plus S will A omega J1 plus A square, J omega square A2. So we want low frequency range, low frequency very close starting. For that, one condition is very clear. B0 should be equal to A0. Okay. When frequencies are very small, this we can neglect. Still low, we can neglect this one. So very close to the that is DC side, A0 should be equal to B0. Then let us take from this one the modulus of this is the closed loop transfer function. This is our f j omega. Now let us take the modulus. This we can again write, this one write as A0 divided by A0 minus A2 into omega square plus j omega A1. Okay. So we can multiply the numerator and denominator by minus j omega. So this again will be equal to f j omega will be equal to A0 into A0 minus A2. So for this here, if you see A0 minus A2 omega square, so omega square is not coming with A2, so this is, let me correct it, this is omega square. So the square is coming here. So A0 minus A2 omega square minus j omega A1 divided by A0 minus A2 omega square plus j omega A1 into again A0 minus A2 omega square, here minus j omega A1. So from this one we can find out the modulus. Modulus fj omega will be equal to root of, we can simplify this equation, finally it will come to A0 square divided by A0 square plus omega square into A1 square minus 2 A0 A2 plus omega square A2 square. This is the modulus. Now let us see how we can control this one so that the bandwidth can be increased. So low frequency A0 square A0 1, you will have modulus of 1. Now as the frequency increases, okay, this term to disappear, still we want slightly higher frequency, it should be 1. The condition is B0 is equal to A0. The second condition from here, we want this to disappear. So that means A1 square should be equal to 2A0 A2. Okay. This we cannot do it. So when the frequencies, for the frequencies where omega it would come, when this term come into picture, so it will slowly drop. So the final transfer function or final modulus fj omega, the modulus of this one, if you substitute this one for this second order, will be, that is the optimum. We have optimized this second order. So f j omega optimum is equal to root of 1 by 1 plus omega raised to 4 A2 by A0 square. So by choosing these parameters, see this second order system we can optimize so that for wide frequency range, that is the maximum we can get a modulus of 1. That is, input will, for any frequency variation of input, output will closely track the input. So this is one way. Now let us take a third order system, because all our purpose is to optimize and choose the controller, PI controller parameter for our voltage loop. So let us take the third order system now. Now we are talking about third order. A general third order system. Omega is equal to B0 plus j omega B1 by A0 plus j omega A1 plus a square term j omega square A2, this is 2 plus j omega cube A3. Okay. So seeing the numerator, one condition for low frequency range, the condition is B0 should be A0. Also B1 should be equal to A1. Okay. Now let us rearrange this one. F j omega, that is equal to, substituting this A0 plus j omega A1 divided by A0 minus omega square A2, because minus comes because of this j square, plus j omega into A1 minus omega square A2. Okay. Now multiplying the numerator and denominator, the complex conjugate of the denominator, okay, and finding out the modulus. So here if you do it, fj omega modulus will be equal to root of a0 square plus omega square a1 square divided by, this is modulus we have found out, a0 square plus omega square into a1 square minus 2a0 a2 plus omega raised to 4 into a2 square minus 2 a1 a3, then one more time is there, plus omega raised to 6 a3 square. So this is the overall denominator. Now how do you do the modulus sucking? Bandwidth, you want as close as possible. Okay. One condition here, a1 square should be equal to 2a0 a2. So one condition. From this, in one condition is equal, already we said a0 is equal to b1 is equal to a1. Now the next condition is equal to a1 square is equal to 2a0 a2 and a2 square is equal to 2a1 a3. With this one, what is the final output transfer function? So based on this condition, the final modulus will be, well, let's go to a new page, will be fj omega is equal to root of 1 plus omega square into a1 by a0 square divided by 1 plus omega raised to 6 a3 by a0 square. This way we will get it. So this is the way we can do the for the third order system. Now let us go back to our voltage control loop, this loop. Let us write down the V0 by V0 star. So if you write down the V0 by V0 star, it will be equal to Kn. Okay, I will slightly bring it down again. Kn into 1 plus Stn divided by Stn, then the current transfer function 1 by Ki by 1 plus St, then V by 2 V0 1 by Sc. This is Gs part divided by 1 plus Gs Hs, that is again 1 plus Kn into 1 plus Stn divided by Stn 1 by Ki. This Ki is the current feedback gain. 1 by Ki by 1 plus ST, again V0 by V by 2 V0, V by 2 V0, 1 by SC into KV, our HS, voltage loop gain. Now, let us expand this one. This is simple mathematical manipulations, but we will write down. Let us go to the next page now. Here it will be V0 by V0 star will be Kn into 1 plus Stn into V input V. V is our input mains voltage, V peak value, divided by Ki S square Tn into 2 V0 into C into 1 plus St plus Kn, PI controller gain Kn, feedback gain, this we have to find out, Kn Kv. So, the parameter which we have to find out, we will Kn Kv into V, input voltage V. So, input voltage, make the input voltage source voltage, I will make a subscript here Vs, this is Vs, Vs into 1 plus Stn. Okay. So, again, so if you expand this one, we know this is a third order system. So, this will be, finally, if you do the thing, it will come Vs Tn Kn into S, that is a Laplace, plus Vs into Kn divided by A0. A0 is equal to Vs Kn Kv plus S into Kn Kv Vs Tn plus S square into Ki Tn 2V0 C plus the SQ plus Ki Tn T, this is our current loop time constant T, we know it is 2 Tr into 2 V0 into C into S cube. Okay. This is of the form third order form, transfer function third order form, where this is equal to B0. This is the B0 and this is equal to B0. If you see the transfer function, this is of the form B0 B1, then numerator, this is the A0, A1, this is A2, this is A3. So, we can, one condition as previously, the first condition is B0 is equal to, we have to equate A0 and B1 is equal to A1. Okay. Now, if we equate the previous conditions, What we have to find out? We have to find out the value of Tn and Kn. All other things are known. So, let us use the previous condition. What was the previous condition? A1 square is equal to 2 A0 A2, and then the next one is A2 square is equal to 2 A1 A3. We can equate the condition. Here Kn, Kv, Vs, Tn square is equal to 2 into Kn, Kv, Vs into Ki, Tn, 2V0 into C. Okay, two unknowns, we require two equations. So, from this one we can get the equation Kn is equal to 4 Ki V0 into C divided by Kv Vs into Tn. And from the second equation, Ki Tn 2V0 C square is equal to 2 into Kn Kv Vs Tn into Ki Tn T 2V0 into C. Okay. From this one, so from this equation also we can find out Kn is equal to Ki V0 C divided by Kv Vs into T. So, from this equation we can find out Kn, substituting here we can find out Tn. So, this way we can find out the closed loop transfer function for the voltage control also. Now, if you go back to your old closed loop control scheme, see here we said IS is given. IS is, if you see the closed loop controller schematic, old one, this IS is multiplied by a sine wave. But all our controller we are assumed the sine frequency is very high, so that during that sine triangle period where the control is initiated, the input current, output current, that amplitude during that period is nearly constant. But if you see, these are sinusoidal waveform, sinusoidal feedback, and throughout the operating condition this frequency of this is constant, but it is going through a controller and converter, so it can create a lag. So, finally to control, to fine tune it, we can give a small lead network here, so that sine can be seeing the waveform, we can give a sine lead, so that the feedback lag can be compensated here. Okay. So that the IS and our Vs will be in phase. So, this we can do. This we can do it. Now, what I want to know, I want to take a typical example and find out the parameter, and I want to model it through MATLAB and Simulink, and I want to show it to you how it works. Okay. So, let us take a typical specification for a front end converter for traction applications, and from then let us design our parameters. These parameters we can use it for controller design. So, let us go to the next page. Say design. Design the parameters. And the component value, parameters of the controller and also the first design the components L and C. Let us take an input voltage, because this is what I simulated. Input voltage peak value 1432 V, and one output V0 equal to 2800 VDC. Let us take our switching frequency, that is a triangle frequency. into 11 times. 60 is the fundamental and our triangle frequency is 11 times the fundamental frequency. This is equal to 660 Hertz. Rated power 1400 kilowatt, and DC link capacitor, assuming a 5% ripple, DC link capacitor can be designed. How to design the DC link capacitor? DC link capacitor we can design from the 5% ripple. The total DC, that 5% of 2800 volts only, and the ripple is due to the second harmonics of the mains, 2 times the second harmonics frequency. So that is the one we have to use it. So we already derived the equation. From the equation we can find out L and C, and once the L and C found out, using the standard technique used for the modulus, again we can find out the control parameter for the PI controller, and already we know that control parameter for the current is simple gain based on the L and the gain converter gain G and the triangle frequency. So this we will take up in the next class.